Okay, now let me continue. So we define using the category of three-term homotopy complex over A. We define exact digit categories, and then state the embedding theorem and this basic property. So we assume our digit category A is additive. So its H0 is additive as a K category. Then exact structure on A is given by a class of three-term homotopy complexes in A, which are homotopy short exact. So the objects in this class will be called conflations, and these conflations will define the bimodule Z in H0 of A. So here, the morphisms which appear here will be called inflations, and the morphisms appear here will be called deflations. And such a class of morphisms, a class of objects, is required to be closed under isomorphisms in this category, and satisfies the following axioms. The first, deflations is first, the identity of zero is a deflation. So this is a homotopy short exact sequence in S. So all are zero. And the deflations are closed under compositions. So for any morphism P, which is a deflation, and P prime, which is also a deflation, then the composition is also a deflation. But notice here that we may have many compositions. Yes, if we have P and the P prime, and we have a composition, this is up to homotopy, then this, for any representative, it is a deflation. Okay, because here is in Z0, okay? And here Q is in a homotopy class of a morphism. So any representative is a deflation. Now, any cospan here, where this morphism is inflation. So here we have a conflation here. And for such a cospan, we have a homotopy push-out. Okay, and the homotopy push-out of the inflation remains a inflation. And dually, deflations, that means homotopy pullbacks, and the homotopy pullback of deflation is a deflation. Okay, and we call such a pair additive digit category A, and such a class satisfying these axioms an exact digit category. Okay. Now a morphism in HQE between exact digit categories A and B is exact if this morphism sends objects in this class to objects in this class. Okay. So directly from the definition, we can give the definition of this exact digit category. We can define this bimodule E over H0A. So A and S be an exact digit category, and A and C two objects. And we have, suppose we have two conflations with fixed ends A and C in this digit category A. And the middle term varies, B1 and B2, and this morphism varies. And suppose we have a morphism from X1 to X2 in this three-term, a category of three-term homotopy complexes over A. And it is an equivalence of conflations if it restricts to identity of A. So such a morphism is given by this. Yes, we can restrict to the objects here. Yes. Okay. Now we remark that an equivalence of conflations is necessarily an isomorphism. So the middle term, so the middle morphism in this equivalence is also an isomorphism. Then we define the bimodule E, which acts on C and A, to be the set of equivalence classes of conflations with ends C and A. And the correspondence S will be given by sending an element in this bimodule, which is given by an equivalence class of conflations to the corresponding conflation in H0, okay? So here, F objects are sent to identity, and the morphism are sent to their homotopy classes. And because DH is composition of these two, so the composition of these two is 0. Then we can verify this directly, that this triple H0 of A and the bimodule E and the corresponding S forms an X triangular category in the sense of Nakaoka and Palu. Okay. Now we state the embedding theorem. So there, for an exact G category A, there exists a universal exact morphism from A to a pre-triangulate DG category. And we denote this by DB DGA. And when this morphism is connective, it is connective if and only if its truncation is quasi-equivalent to itself. Then this morphism is quasi-fully faithful and quasi-fully exact. So namely, this morphism induces a quasi-equivalence from A to the truncation of a certain extension closed subcategory D prime of this pre-triangulate category. And it's quasi-fully exact means that this morphism induces bijections between this module over H0 of A and this extension 1 of this triangulate category. And this triangulate category is just H0 of this pre-triangulate DG category. Okay, so combining these two, we can just say that F induces an equivalence of exact DG category between A and tau 0, tau is equal to 0 D prime. And we call this pre-triangulate DG category the DG derived category of A. Yes. When A is equivalent exact category, then the DB DGA is the canonical DG enhancement of the canonical bounded derived category of A, of the equivalent exact category. So that's why we call this the DG derived category of A, and this notation. We also have corresponding analog theorem for exact infinity category is due to Clément. And as a consequence of this embedding theorem is that H0, we have another proof of that this triple H0 of A and the bimodule and the correspondence is X triangulated. Yeah, that's because our H0 of A will be extension closed subcategory of DBA of a triangulate category. And thirdly, here we computed X1 in this triangular category between objects in A, in H0 of A, we can also compute these higher extensions by the tensor power of the H0A bimodule E, and it's given by Gursky, Nakalka, and Palu. So we can indeed compute these higher extensions. Now let's start the examples. Throughout, we'll assume A is additive DG category. Okay. When A is concentrated in degree 0, then the exact DG structure is exactly the equivalent exact structure. So why? That's because we have shown that homotopy left, right, or blank exact sequences are the same as left, right, or blank exact sequences in A. And homotopy pullbacks are the same as pullbacks, and homotopy pushouts are the same as pushouts. So we can rewrite our axioms. So our axioms will be the same as equivalence axioms. So that's why we have this equality. Okay. The second class is when A is pre-triangulated, then the class of all homotopy short exact sequences is namely the class of all graded split short exact sequences. This will define an exact structure on A, and it's not hard to check this fact. As an example, when E is an additive category, then we can take its pre-triangulated R, so the bounded complex, the DG category of bounded complexes over E, and here the homotopy short exact sequences are the three-term homotopy complexes that are isomorphic in this category to the graded split short exact sequences of complexes over E. So we have short exact sequences of complexes, and it's graded split. So these two are not morphisms of complexes. They are just graded maps. Now, for any extension closed subcategory of an exact DG category, it will naturally inherit an exact DG structure. So, and a full DG subcategory is called extension closed if for any conflation in A. So this belongs to S. And whenever these two objects are in this full subcategory, then we have the middle term also lies in this full subcategory. Then the exact structure on this full subcategory will be given by the conflations in A, where all three terms are in B. And the reason that this forms an exact structure on B is as follows. For example, when we try to verify axiom EX2, we want to show that the inflations in B have admits homotopy pushouts, and the homotopy pushouts remains inflations remains an inflation. And the reason is as follows. We can form such a diagram here. We have this, and this is an inflation in A, and this is a morphism. Then, as in the ordinary category case, we have another three-term homotopy complex here, and a morphism between these two homotopy complexes, where this is identity, and this is a homotopy pullback, this square. Okay. Now, because this morphism is an inflation, and this object is a homotopy short exact sequence, then this will be a conflation in A. So, and because A prime, A, B, and C are all in B, in particular, these two are in B, so B prime also lies in B. So, so this says that axiom EX2 also holds in B. Sorry, I missed Bacon's question. Yes, Bacon asked whether there is a direct construction of this category. Yeah, we construct this this morphism by first embedding A into the pre-triangulated R, and then we perform the DG quotient of certain DG subcategory, and this DG quotient is a DG derived category. Yes. Yes. Thank you for the question. Yes, let's continue. Okay. Now, the notion of exact structure is self-dual. So namely, if we have a conflation in A, we have these three-term homotopy complexes, then we can get a corresponding diagram in the opposite of A, and then we perform. We have a canonical automorphism, a canonical isomorphism between B and the B op, where B is the where B is this category, this path category. And we have a canonical automorphism here, and it is opposite. We can send this vertex to this vertex, and this to this, and keep the middle one. Okay, and so we get this should be A, and hence we get three-term homotopy complex in A op. Okay, so so from an exact structure on A, we get an exact structure on the opposite of A. Okay. And when we check the definitions here of exact structures, we see that here the morphisms are in Z0 of A, and the property of this, the definition of these homotopy push-outs, homotopy pull-backs, and the homotopy short exact sequences only involves the negative part, the truncated part of A. And so the exact structures on A will be the same as the exact structures on the truncation of A. And the diagrams remain in the truncation of A. And we don't change H0 of A, and we don't change the bimodule E, and we don't change the correspondence. So actually we change nothing when we replace A by the truncation of A. Okay. And then we have the minimal exact structure on an additive DG category. So the class of all split short exact sequences. So so here that is isomorphic to split short exact sequences. Okay, so this will split in Z0 of A. And a theorem is that each additive digit category also admits the greatest exact structure, namely the unique maximal exact structure. And this theorem generalizes a result due to Hooft. And an important property of exact digit structures is that it can be transferred along quasi-equivalences. Yes, that this is because that yes, we defined our homotopy 3-term complexes to be invariant under homotopies, not strict digit functors. So it can be transferred along quasi-equivalences here. HQE, yes. Our category are defined based on HQE, so it's invariant under these homotopies. Now, for a pre-triangulated G category A, you can take this truncation. Then it is stable, namely it has homotopy kernels, has homotopy co-kernels, and any 3-term homotopy complex in A is homotopy left exact if and only if it is homotopy right exact. Okay, then endowed with the structure, exact structure given by all homotopy short exact sequence in this truncation, then we recover the pre-triangulated G category of A by its bounded digit direct category. But yes, so connective digit category is never pre-triangulated. Yes. But it can also happen that a non-connective digit category, which is not pre-triangulated but is stable. So examples are given by Yama and Young's construction. A special case of their construction. So suppose we have a pre-triangulated DG category and a thick subcategory. And in the thick subcategory S, we have a T structure given by X and Y. And we take the pair of subcategories in T given by X and the right orthogonal with respect to Hooft spaces of X and Y and the left orthogonal of Y with respect to Hooft. And then we say that we assume these two pairs of subcategories are T structures in P. Then this 4DG subcategory of T is stable. Here is given by the intersection of these two of right orthogonal of X and the shift of left orthogonal of Y. Okay, but this Z is usually not pre-triangulated. And we take this structure, the exact structure, because it's stable, here it is stable, and we take the class of all homotopy short exact sequences in Z, then and its bounded digit derived category is this DG quotient. Okay, and concrete examples of this setting is given by Hypogenes simple-minded collection reduction. Okay, and now I would like to show that why Z is stable. Yes. So I will check that Z has homotopy kernels and homotopy co-kernels, and 3-term homotopy complexes in A is homotopy left exact if and only if homotopy right exact. So first, we take a morphism in Z. So G, a morphism from Z1 to Z2. Then we take this triangle in T. And because we have this T structure in T, so we have this triangle in T, where this object lives in the shift of Y. And this object, we can check that this object now lives in Z. Yeah, because here F is in the right orthogonal of X, and Y is in the right orthogonal of X. And so as an extension of F and Y, Z0 is in the right orthogonal of X. And because we take this triangle using this T structure, so this lives in the left orthogonal of Y. So it lives in the so it is in Z. Okay. Now we claim that this sequence is a homotopy left exact sequence, and we can check this as follows. Yes. So this sequence is yeah, we can view this as if when we apply hom blank that belongs to this sequence, then we can view this as the shift inverse of the cone of this morphism. So we only have to show that for objects Z here, there always exists a unique map here, such that this commutes. But this can be checked by using this orthogonality. So I think we can leave it as an exercise to check this. And homotopy kernel is by duality. So we take a morphism here, and we form its cone in T. Then we use this structure. Then here. Then we can show that this object lives in Z, and this sequence is homotopy right exact. And to show that a switch-term homotopy complex is homotopy left exact, if and only if it is homotopy right exact, we use the octahedron axiom in T. Yes. So because we start Z0, Z1, Z2, this sequence. And because we assume it's homotopy left exact, then by our first construction of homotopy kernel, this morphism is given by this diagram. So we take the mapping cone, the shift inverse of the mapping cone of G in T. And we have a unique map here. And we have such a diagram given by this. Okay. And now we want to show that when we compose this morphism and the form and using this construction, and we form its mapping cone, and we want to show that this this triangle is given by this T structure. Yes. And I think yeah, I have checked it here. So yeah, here by octahedron, this is an object in shift 2 of Y. So here, this object in shift of Y, okay, it is shift of Y. So in particular, it lies in the 6th subcategory S. Okay, so we only need to show that this object is in the left orthogonal of Y, but we can check this by showing that C and the shift inverse of Z2 is in this category. So I think this can be checked easily. So this Z is homotopy is stable, and so is H0 of Z is triangulated. So here we obtain the triangle structure of H0 of C in terms of this exact digit structure on that. Now, let me give another more general example of T structures. Okay, so for an additive digit category A, it is left stable, or in Lurie's notion is pre-stable. So it is left stable if it has homotopy push-outs. So in particular, we have suspension morphism from the digit category A to A. And at the level of objects is given by sending A to the suspension of A. And suspension of A is given by this homotopy push-out of this span from A to 0 and to 0. And secondly, each homotopy push-out is also homotopy pullback. This means that homotopy push-outs are homotopy bicartesian, but not every homotopy pullback is homotopy bicartesian. Okay? But for this step, from an object B to the suspension of an object in A, we have such a homotopy bicartesian square. Yes. Okay. Now, when the additive digit category A is pre-stable, we can define an exact structure on A. So we simply take all homotopy short exact sequences in A. Now, the key to prove this is that for any map from B to the suspension of C, we will have such a morphism between homotopy short exact sequences. Yes. Here for suspension of C, we have such by definition, we have such a homotopy bicartesian homotopy short exact sequence from C to 0 to the suspension of C. Okay, and then we can by this condition, we can form a homotopy bicartesian square D to B to shift C and to 0. This is homotopy bicartesian. And then by the universal property of this one, this is in particular homotopy pullback, and we have this here, can take 0. Then by the universal property of homotopy pullback, we have a we can form such a diagram. Okay. Now we need to show that this is homotopy bicartesian, homotopy short exact. But if we don't have such conditions, then we can't show this. So we leave it as an exercise to show that this is indeed homotopy short exact sequence. Okay. And this is important in checking this. This defines an exact structure. Now, as a consequence, the suspension morphism sigma from A to A is quasi-free faithful. Yes, this is because from this maybe truncation of A. Yeah, truncation of A. Yes, this is because we have our embedding theorem from truncation of A to its DG derived category. And here the suspension of truncation of A will translate into the suspension in the triangulate category. And here the suspension is fully faithful. So we get that this suspension morphism is quasi-fully faithful. And this is the original definition of Lurie. Here he do not require this, he just require this suspension morphism is quasi-fully faithful. Yeah. But we do it in a reverse way. Okay. So as examples, T structures will give rise to pre-stable DG categories. The L will give rise to pre-stable DG categories. Okay. So in a pre-triangular DG category T and the T structure AB, then A is maybe left stable. And then we take the exact structure above. We have taken all homotopy short exact sequences, and then we have a unique morphism from the derived category to T induced by the inclusion of truncation of A into T. Because this morphism is an exact morphism, and this T is pre-triangulated. So we have a unique induced map. Okay, and when A is pre-stable, then it has enough injectives. And because it has enough injectives, we can compute its higher extensions. So that's why we can prove it's quasi-fully faithful here. Now we check that this is really pre-stable. First, because A is stable under shift and the suspension in the pre-triangular category T, so automatically it has homotopy kernels. And at the level of homotopy kernel, starting from a morphism in this DG category A, we can form this shift inverse of mapping cone, and in the DG pre-triangular DG category T, then we use this T structure. So this is in A and this is in B. Now this composed map and this morphism G is homotopy left exact. Yeah, we can check this because for any object A here, this vanishes. So there is a map here, and from A to the shift inverse of B also vanishes. So this map is unique. So this is a homotopy left exact sequence. And other axioms here are easy to check. Now a proposition is set if A is pre-stable and admits homotopy pullbacks. So these are properties of the additive DG category. It's not a structure. Then we can show that this truncation is indeed L in a pre-triangular DG category. So the embedding of this exact DG category endowed with all homotopy short exact sequences embed into bounded digit-derived category, we'll identify it with an L in the pre-triangle digit category A. And the idea of this of the proof is that objects in the heart can be determined by the homotopy kernels of the adjunction morphisms. Yeah, because A has homotopy proof X, so it also admits a loop morphism from A to A, and we have a adjunction morphism for each object X in A. We have an adjunction morphism. Then its homotopy co-kernel will be an object in the heart. Okay, so it's an exercise to check this in the case of T structures. Okay. So when we have this heart, then we can give the T structure. Okay. Now let me end with a proposition. So my aim is to show the following. Each connective additive digit, each connective exact digit category is of the form of a Quillen exact. Is of the form of a digit quotient of a Quillen exact category by a full subcategory of projective injectives, and then for each additive connective DG category, so this, and we take is minimal exact structure, then we can show that it is of the form of the DG quotient of an additive category by a full subcategory. So these categories are concentrated in degree 0, and we recover all, we get all DG categories by DG quotients of a category concentrated in degree 0. And we need this proposition. So we consider a connective exact digit category A and a full subcategory of projective injectives. Then we have this commutative diagram. We start with the triangulated triangle hull of A. Then the quotient map to the bounded derived category of A. And we can also pass to the triangulate hull of the DG quotient of A by P0. And both can pass to the bounded derived category quotient by the triangulate subcategory generated by P0. Yes, and we can show that the morphism, the functor H is fully faithful. And for each, yes, we can say more here. Yeah, C3 is stronger than 1. So here, for n less or equal to 0, the negative extensions between A and B is isomorphic to the negative extensions between A and B between these two categories, and objects are in A. Okay. And for between these two categories, the higher extensions, higher than 1, are isomorphic between objects in A. Okay, so this means that because this is the DG quotient of A by P0, this means that this canonical morphism into a pre-triangulated DG category is quasi-fully faithful and closed-end extensions. So in particular, it inherits an canonical exact structure. and its H0 is the ideal quotient here. And so this DG category, has a canonical DG structure, and yeah, and this is a corollary of this proposition. Okay. I think I will stop here.
Thank you very much for your excellent lecture. Are there any questions or comments?
Sorry, may I ask a question just in the last corollary? What happens if the E by chance be a Frobenius exact category?
Then this is Frobenius exact DG category.
Ah, yes. So we have the notion of the Frobenius exact DG category, yes?
Yes, I think it's analogous to the Frobenius exact category. Yes. Yes, I think the last corollary might be useful when studying DG localizations of exact DG categories. Okay. The homomorphisms are inflations. I'm not sure the last one holds. Yes, I don't know why this morphism will have a kernel here. Yeah, honestly, I don't know the answer. But thank you for the question. Yes, I think these two will hold. Yeah, but I don't know this one.
Are there any further questions or comments? If not, let's thank Xiaofa again for very nice lecture, and also all speakers of this seminar. Thank you all for attending this 3-day online seminar. We hope that we will see you in the similar event in the near future, hopefully in person. See you.
Yes, thank you.
Xiaofa, could you please send me your notes?
Yes, I will send them by email.
Yes, thank you very much. Thank you.
Yes.
Yeah, thank you very much for your nice presentation.
Yes, thank you for the invitation once again.